Welcome to This Explainer. Today, we're embarking on a seriously wild journey to understand the high-stakes mechanics of actually getting to space and, just as importantly, safely returning to Earth. You know, going to space isn't just about floating around in zero gravity and looking at the stars. It's an intense, absolute battle against the laws of physics. So let's dive right into how human beings actually manage to leave our planet, survive the incredibly hostile vacuum of space, and make it back home in one piece.
Now, before we look at the engineering triumphs, we really need to ground ourselves in the absolute reality of the dangers involved here. Space travel is, without exaggeration, a matter of life and death. Back in January 2003, NASA's Space Shuttle Columbia launched on its 28th flight. On board were 7 highly skilled astronauts, including India's Kalpana Chawla. And for 16 days, everything was practically perfect. They conducted all these groundbreaking scientific experiments in a controlled zero-gravity environment. But on February 1, 2003, right as they were scheduled to return, disaster struck. During atmospheric reentry, ground control suddenly lost communication. And shortly after the horrifying truth emerged, the Columbia had disintegrated. Everyone on board was lost. Going up into space is one monumental challenge, for sure. But as this absolute tragedy reminds us, coming back down is an incredibly perilous journey.
All right, let's move into Section 1, the vehicles, and exactly what gets us up there.
There's this super common misconception that the words rocket and spacecraft can basically be used interchangeably, but actually they are completely different things with entirely different jobs. Think of the rocket as the taxi. Its only job, literally its entire purpose, is to provide the immense power, the sheer brute force and thrust needed to break free from Earth's gravity and get you to your destination. The spacecraft, on the other hand, is the passenger cabin. This is the actual living quarters. It's the sophisticated high-tech module that safely holds the astronauts, the life support systems, and all that scientific equipment. You absolutely need both. The rocket is the muscle, the spacecraft is the brains and the shelter.
So how does that giant taxi actually get off the ground? Well, it all comes down to Newton's third law of motion. For every action, there's an equal and opposite reaction. A rocket engine burns a massive, and I mean massive amount of fuel, creating intensely hot gases that it blasts downward out of its engines. That incredibly violent downward action creates the immense upward reaction, the thrust, that lifts thousands of tons of metal straight up into the sky.
Now, you might be wondering, why can't we just fly a really fast airplane into space? Why do we need the massive rockets? Well, an airplane engine is essentially an air-breathing machine. It sucks in oxygen from the Earth's atmosphere, mixes it with jet fuel, and burns it to create thrust. But as you get higher, the air gets thinner and thinner, until eventually in space, there is absolutely no air at all. It's a vacuum. A jet engine would instantly choke and die. Rockets solve this problem beautifully. They pack their own air. They carry massive internal tanks of both fuel and oxidizer, which can be liquid or solid propellants. Because a rocket brings its own oxygen supply, it doesn't care that space is a vacuum. It can burn its fuel and create thrust literally anywhere in the universe.
Of course, you can't just stand a rocket up in a random field and light a match, right? You need the third essential piece of the puzzle, the launch pad. This isn't just some giant metal stand. It is a highly complex, precision-engineered megastructure. Its job is to hold the rocket, fuel it, and ensure it is projected in a perfectly straight line toward the sky at the exact right moment. Everything is timed down to the literal millisecond based on the weight of the payload and the incredibly complex orbital mechanics required to get the spacecraft exactly where it needs to go.
And this all builds into the actual launch sequence. Step 1 is that thunderous, earth-shaking ignition at the launch pad. Step 2 is liftoff, where the main engine and those massive side booster rockets fire together to fight gravity. But Step 3 is where it gets really clever. Those side boosters are usually filled with solid propellants. Once that solid fuel burns out, those boosters are nothing but massive empty metal tubes, just dead weight. So to save energy, the rocket simply detaches them, letting them fall away. Finally, in Step 4, once the spacecraft reaches the correct altitude and speed to enter orbit, the main engine detaches too. The taxi has completed its job and it drops away.
Once that rocket falls away, the entire dynamic changes. The spacecraft is now flying solo in orbit. At this point, the astronauts can actually take manual command of the spacecraft. It's kind of similar to a pilot flying an airplane, but instead of using a windshield to look for clouds, they rely on incredibly advanced sensors, navigation arrays, and constant communication with ground control. And most of our human spaceflight today actually happens relatively close to Earth, in low Earth orbit. The astronauts navigate their spacecraft to dock with facilities like the International Space Station, the ISS, which acts as this amazing orbiting laboratory and hotel where they can live and conduct experiments for months at a time. Which brings us to Section 2, the return, and why it's such a perilous journey home. I want you to burn this number into your mind for a second. 17,500. That is the speed, in miles per hour, that a spacecraft is traveling as it orbits the Earth and begins its descent. They don't have that massive rocket anymore to slow them down, so they have to use the Earth's atmosphere itself as a brake. I mean, imagine hitting the air at 17,500 miles per hour. The air physically cannot get out of the way fast enough. It compresses violently against the bottom of the spacecraft. And that extreme compression and friction, it creates a literal wall of superheated plasma. We are talking about temperatures hotter than melting steel. This brings us to what is arguably one of the most critical pieces of engineering in human history, the heat shield. This is a specialized, highly heat-resistant layer covering the bottom surface of the spacecraft. It is the only thing standing between the astronauts and absolute incineration. It absorbs and deflects all that intense thermal energy. Connecting this back to our opening story, the Space Shuttle Columbia disaster was actually caused by a piece of foam damaging this very shield during launch. When they tried to re-enter, the superheated gases breached that damaged shield, leading to the tragedy. It is a vital, totally non-negotiable lifeline. But assuming the heat shield does its job perfectly, here are the final steps of the landing process. First, they survive that fiery atmospheric re-entry. Second, as they get closer to the surface and the air thickens, the spacecraft levels out to become parallel to the Earth, bleeding off even more speed. Third, they deploy specialized rear parachutes to drastically cut their velocity. And finally, they land. Now, older missions, like the famous Apollo moon landings, used what we call a splashdown, landing directly in the ocean. While it definitely provides a soft cushion, it carries a very real sinking risk if a hatch blows or the capsule gets swamped by a wave. Because of that danger, returning to a hard runway is highly preferred whenever the vehicle's design allows for it. Moving right along to Section 3, survival gear and the colors of space. Every single detail in space travel has a life-saving purpose, even the fashion. Have you ever wondered why astronauts wear different colored suits at different times? It's all about visibility and survival. The orange suit, which is known as the Advanced Crew Escape Suit, is worn strictly during the highly dangerous phases of launch and landing. Why orange? Well, because it is the single most visible color against the blue ocean or Earth terrain. If there's an accident and they have to bail out, search and rescue teams can spot that bright pumpkin orange instantly. Plus, these suits are packed with survival gear, a parachute, a knife, and a water-activated strobe light. Conversely, the bulky white suit is worn during spacewalks outside the craft. Why white? Because white reflects the harsh, unfiltered radiation of the sun, and importantly, it is highly visible against the pitch-black void of deep space. So, we've seen how incredible, yet completely dangerous and, frankly, wasteful this process has historically been. I mean, literally dropping multi-million-dollar booster rockets into the ocean after a single use. But the paradigm is shifting so rapidly right now. Private companies like SpaceX with their Falcon 9 and national organizations like India's ISRO are pioneering fully reusable rockets. Instead of becoming extremely expensive trash, these incredible machines launch their payloads, detach, and then autonomously fly themselves back down to land upright on Earth, perfectly ready to be fueled up and flown again. It's an absolute revolution in aerospace engineering. It really makes you wonder, if we can now recycle the very rockets that take us to the stars, making spaceflight cheaper and more frequent than ever before, what incredible discoveries are waiting for us just over the cosmic horizon? Thank you so much for joining me for this explainer on the science of space travel. Keep asking questions and keep looking up.